When you look at a linear accelerator, it looks very quiet and peaceful. But at the atomic level, it is an absolute war zone. Inside the machine, electrons are being fired like high-speed bullets. When high-speed bullets hit the heavy metal target, two completely different events happen. One is a chaotic, massive braking collision called as Bremsstrahlung X-ray radiation production. The other is a electron ejection called as characteristics X-ray radiation production. Most residents just memorize these names for their exams. They read the textbooks, but they completely fail to understand the physics behind these two important interactions. Not anymore. Today I will teach you exactly what happens when high-speed electrons strike an atom of tungsten target material within an X-ray tube. I will make this physics simple for you. After watching this lecture, you will never look at an X-ray beam the same way again. Pay very close attention. Hello friends, before we begin, for those who are new to this channel, I am Dr. Parveen Ahlawat. I am a consultant at Rajiv Gandhi Cancer Institute and Research Center in New Delhi for over 12 years. I have been practicing and teaching oncology for more than a decade. I did my MBBS and post-graduation from CMC Vellore. Then I did my DNB at Rajiv Gandhi Cancer Institute and Research Center, New Delhi. I pursued a fellowship at Royal Marsden Hospital in London and have later undergone specialized training in cyberknife from the United States. I have published almost 85 research articles and abstracts in PubMed Index international journals. Welcome back to our series of lectures on radiation physics. In our previous lecture on X-ray tube, we thoroughly explored the structure and functioning of an X-ray tube. If you have not watched that video, you must do it before watching this video. Let us quickly summarize the exact sequence of events from that lecture. We saw this X-ray tube in our previous lecture. We saw the cathode and its heated filament. We saw how this filament boils off a massive cloud of electrons. These electrons are then vigorously accelerated to extremely high speeds. They travel across the empty vacuum of the glass tube. And finally, they smash directly into the heavy tungsten target, right here. When these high-speed electrons are forced to stop suddenly, a massive conversion of energy takes place. What exactly happens during this collision between the high-speed electron and the tungsten atom is our main topic for today's lecture. The topic of today's lecture is X-ray photon production by two main mechanisms, Bremsstrahlung radiation and characteristic radiation. Today's lecture is going to be a long video because there are many important concepts which require time to explain you. Let me summarize today's lecture right here. The moment this collision happens, the kinetic energy of those high-speed electrons is converted into different types of energy. Now listen carefully. In a standard low energy machines such as diagnostic X-ray tube, over 99% of this kinetic energy is completely wasted as pure heat. See here. Only less than 1% of that energy is actually successfully converted into useful X-ray photons, which is used to take diagnostic images. So, in a diagnostic X-ray machine, the ratio is 99% versus 1%. 99% energy is lost as heat, and the remaining 1% becomes X-rays, which we use clinically to take diagnostic images. However, in a high energy therapeutic machines such as our linear accelerators, this ratio of energy conversion is much more efficient. In high megavoltage energies such as our linear accelerators, the efficiency of X-ray production jumps from less than 1% to an incredible 30%, sometimes even to 90%. This X-ray photon production is created through two processes. Primarily through a process called Bremsstrahlung radiation, which constitutes approximately 97%, and the remaining 3% by characteristic radiation. Today, in this lecture, I am going to teach you exactly these two processes, Bremsstrahlung radiation and characteristic radiation. You can call them processes or interactions. Now please be careful and absolutely clear here and don't get confused with these two types of interactions with those three types of interaction which happens between photon and the matter of body. Those are photoelectric effect, Compton and pair production effect. Those are completely different interactions and occur later when the clinically used X-ray beam hit the body and interact with the body. I will teach you those three interactions in a separate lecture. For today, in this presentation, I will teach you fundamental processes, Bremsstrahlung radiation and characteristic radiation, step by step. First, I will show you exactly how the central nucleus creates the continuous Bremsstrahlung X-rays. Then I will explain you how the orbital electrons give birth to discrete characteristic X-ray. Finally, I will teach you how to combine these two mechanisms to fully understand the actual clinical X-ray beam spectrum you will get to treat your cancer patients. Let us begin. Before I start explaining you Bremsstrahlung and characteristic radiation, I want to revise the basic structure of an atom and the binding energy concept. It is important. I know many of you may be knowing it already, but it is important to revise it right now. To understand X-ray production, we need to take tungsten as a typical atom. Let me explain exactly why we choose a tungsten atom. In an X-ray tube, we need a target material. We cannot just use any random metal as targets. We choose tungsten. There are two specific reasons why tungsten is the best choice for X-ray tubes. First, tungsten has a very high atomic number of 74. Having this high atomic number is absolutely essential. High atomic number means larger nucleus. A larger nucleus means more positive protons. A larger nucleus with more positive protons create a much stronger attractive braking force for the incoming electrons. This massive braking force dramatically increases the overall efficiency of our Bremsstrahlung radiation production. Second, tungsten has an incredibly high melting point of 3000 degrees Celsius. I will remind you of what we discussed in previous lecture. I showed you that over 99% of the kinetic energy from electron beam is completely wasted as intense heat. Most normal metals would simply melt or get destroyed under this extreme and intense heat. Because tungsten can easily withstand this intense heat without being destroyed, it is the perfect target material for our X-ray tube. Before I teach you how radiation is produced, you must perfectly understand the structure of atom. Notice the dense cluster in the center of the atom. This is the nucleus of the atom. It contains positive protons and neutral neutrons. Tungsten is a very heavy metal with an atomic number of 74. This means there are exactly 74 positive protons packed tightly inside this nucleus. Now look at dots of black circles around that central nucleus. These are orbits, also called as shells. You can also see green colored dots. These are the negatively charged electrons. These electrons do not float randomly, but rather stay in their respective orbits or shells. The shell closest to the nucleus is always called the K shell. As we move outward, the shells are named subsequently as the L, M, N, O and P shells. The interaction between high-speed negative electrons coming from the cathode and the nucleus or orbital electrons of the anode target made up of tungsten atom is what creates our X-rays. Let me explain the invisible forces that holds this entire atom together and keeps it stable. Look at this diagram. This diagram represents a detailed cross-section of the tungsten atom. You can clearly see the central positive nucleus, this one. Curving around this nucleus are the orbits or shells. These shells are labeled sequentially from the inner K shell moving outward to N shell. Now let me introduce a very important concept called binding energy. Binding energy. I taught you about binding energy in my previous class. Understanding binding energy is mandatory here for today's topic. See, binding energy is the exact amount of energy required to completely release an electron from the atom. Once again, binding energy is the exact amount of energy required to completely release or eject an electron from the atom. Think of it as a strong, invisible, attractive force acting between the positive protons in the nucleus and the negative orbiting electrons. There are two major factors that determine the exact strength of this binding energy. First, it depends entirely on the atomic number, which is the total number of positive protons. A nucleus with a high number of protons create a much stronger electrostatic pull on all of its electrons. Second, the binding energy depends on the distance between the nucleus and the electron. Distance. You can see here the binding energy of various shells, these. Notice carefully, the binding energy dramatically increases as the orbits gets closer to the nucleus. Do you notice that? Look at the specific energy on each shell. The outer N shell is far away from the nucleus and has a very weak binding energy of just 0.6 keV. M shell has slightly higher 2.5 keV. L shell has 10.2 keV. Now look at the innermost K shell. K shell is held very tightly with a massive binding energy of 69.5 keV. Let me explain exactly what this unit keV means in our physics module. Radiation oncologists often get confused with this unit. They are familiar with joules as a unit of energy but not keV. You will see this term everywhere in your textbook and even in this lecture. The letters keV stands for kilo electron volt. Before we look at the kilo part, I will teach you what a single electron volt actually is. An electron volt is simply a very small number of energy. Measurement of energy. It is the exact amount of kinetic energy that one single electron gains when it is accelerated across an electrical potential of exactly 1 volt. Because atomic energies are very small, using standard units like joules is completely impractical for our calculations. Therefore, we use the electron volt as our fundamental standard unit for atomic energy. The letter K stands for kilo, which means 1000. So 1 keV, that means 1 kilo electron volt is equal to 1000 electron volts. When we say the K shell binding energy is 69.5 keV, It means electron is held tightly in its place with 69,500 electron volt of energy. This is what keV means. I want you to memorize this specific number, 69.5 kilo electron volt right now. Now look here carefully. This red dot is an incoming electron. It is approaching towards this inner K-shell electron and wants to dislodge it from its position. If this incident electron wants to completely dislodge or eject this K-shell electron, it must possess a kinetic energy strictly greater than the binding energy of this electron. That means at least 69.5 keV. If your X-ray tube machine is set to a lower energy, this inner electron simply will not be dislodged from its atom. Now that you have fully understand this atomic structure and binding energy, I will teach you the exact mechanism of Bremsstrahlung radiation in next slide. Let us first learn Bremsstrahlung X-ray radiation. We will then learn characteristic X-ray radiation. Bremsstrahlung X-ray radiation is responsible for creating the vast majority of your clinical X-ray beams. This is completely true for both the linear accelerators in our radiation oncology department and the standard X-ray tubes in radiology department. Recall X-ray tube. As I mentioned earlier, over 99% of the incoming kinetic energy from electrons from cathode is completely wasted as heat. But a tiny, highly valuable fraction of that energy successfully creates our useful X-ray photons. I will show you exactly how this happens at the atomic level. Let me break down the exact physics of this specific interaction for you step by step. This is again a structure of a stable atom. I said a stable atom. This is how a stable atom looks like before an incoming high-speed electron comes near this atom. As we discussed earlier, this represents our heavy tungsten atom with 74 positive protons packed tightly into the central nucleus. Orbiting around this positive center are the negative electrons, perfectly balanced in their specific energy shells. This target atom right now is currently in a perfectly stable and neutral state. However, when we apply our current tube potential in X-ray tube, a bombarding electron from the cathode is accelerated towards this stable atom. I will show you exactly what happens when a fast-moving, high-speed incoming electron comes near this stable atom. It is this specific microscopic interaction that gives birth to the Bremsstrahlung radiation you will use to treat your patients. Let me guide you through an animation showing how Bremsstrahlung radiation is actually produced. I will show you exactly how this microscopic interaction happens in real time. This is a stable atom, for example, a tungsten atom. Please see this red dot. This red dot represents our incoming high-speed electron arriving directly from the cathode of X-ray tube. See here the X-ray tube we saw earlier and the electrons emitting from the cathode. Watch the movement of this high-speed incoming electron in next slide. Notice how it easily penetrates the outer electron shells of tungsten target atom. It completely ignores the negative orbital electrons floating in those outer layers. It travels deep into the inner orbit, moving through the vast empty space of the atom. Now pay very close attention as this incoming electron approaches towards the nucleus of this stable atom. This high-speed incoming electron is moving very close to the heavy nucleus of tungsten atom. I will remind you that this specific nucleus is packed tightly with 74 positive protons. Because of this massive positive charge, it creates an extremely strong electrostatic pull on this negative incoming electrons. This invisible force of attraction is incredibly powerful at such a close distance. Because of this extremely strong pull, the high-speed electron cannot travel in a straight line anymore. It is forced to sharply bend its path. You can clearly see the electron making this sharp turn on your screen right now. Think of this just like driving a fast car on a highway and suddenly making a very sharp turn. In order to survive that sharp turn, the car must slow down. The exact same physics principle applies to this high-speed incoming bombarding electron. As the electron makes this very sharp turn around the positive nucleus, it is forced to break. Once again, as the electron makes this very sharp turn around the positive nucleus, it is forced to break. Electron is taking a sharp turn and slowing down. Electron is taking a sharp turn and slowing further down. Electron is taking a sharp turn and slowing down further. As this electron slows down, it instantly loses a massive amount of its original kinetic energy. Look at the electron exiting towards the bottom right of the atom. It is now a much more slower electron. It is slower because a huge fraction of its kinetic energy has been completely stripped away by that braking force. But the law of conservation of energy states that this lost energy cannot simply disappear. What happens to this lost energy then? According to the fundamental law of conservation of energy, this lost energy cannot simply disappear. It is completely and instantly converted into an electromagnetic wave. This newly born wave is your Bremsstrahlung X-ray photon. This X-ray produced is called Bremsstrahlung X-ray photon. Remember that the exact amount of energy this photon carries is perfectly equal to the kinetic energy lost by the electron during that sharp turn. Now that you have understood how a single photon is born, we must look at the larger clinical picture. The exact energy of this newly born photon is not the same for every single interaction. It depends entirely on the physical distance between the incoming high-speed bombarding electron and the heavy central nucleus. Because this distance varies completely at random, the strong attractive braking force will also vary. I will show you the three specific scenarios that dictate the final energy spectrum of Bremsstrahlung X-ray. See here. In the first scenario, the incoming electron passes very close to the nucleus. In the second scenario, the electron travels far away from the nucleus. In the third and most rare scenario, the electron makes a direct head-on collision with the nucleus itself. I will show you exactly how each of these three unique paths create a completely different energy photon for our treatment beam. Let me break down these three scenarios for you one by one in the upcoming slides. Let us look at the first specific scenario of Bremsstrahlung radiation. See exactly what happens when an incoming electron passes very close to the nucleus, but not directly hitting it. Please direct your attention to the path of incoming electron. You can see an incoming electron arriving from the cathode with an initial kinetic energy of suppose 100 keV. Watch its path very carefully as it penetrates the outer orbits of the target atom. In this first scenario, the electron travels extremely close to the heavy central nucleus. See here. Because it is so close to the nucleus, it experiences a massive electrostatic pull from the positive protons. This incredibly strong invisible force alters the electron's path sharply. You can see the electron making a very sharp and sudden turn. Just as we discussed earlier, making this severe turn forces the electron to slow down in speed. We can say hit the brakes forcefully. As it drastically slows down, it is forced to lose its kinetic energy. In this specific animation, the braking force is so extreme that the electron loses absolutely all of its kinetic energy. Look at the outgoing electron exiting the interaction with exactly 0 keV of energy. According to the fundamental law of conservation of energy, that lost energy cannot simply vanish. It is instantly converted into a brand new electromagnetic wave. You can see this newly born Bremsstrahlung photon radiating away right now. Because the incoming electron lost its entire 100 keV of kinetic energy, the resulting photon is born with exactly 100 keV. This represents the absolute maximum photon energy that your X-ray tube can possibly produce at this specific kilovoltage setting. So this is what happens when the incoming electron comes very close to the nucleus. In our next animation, I will show you the next scenario. What happens when the electron travels much further away from the nucleus? Notice this incoming electron arriving with a kinetic energy of, for example, 90 keV. See what happens when this electron travels much further away from the central nucleus. Watch its path very carefully as it moves through the atom. Electron entering the outer orbit of this atom. Because the electron is far away, the electrostatic pull from the positive protons is significantly weaker. This weaker invisible force only alters the electron's path slightly. You can see the electron making a much more gentle curve compared to our previous scenario. Because it makes a gentle turn, it does not have to hit the brakes as hard. Look closely at the outgoing electron exiting toward the bottom right. Therefore, it only loses a small fraction of its kinetic energy. It retains a large portion of its original energy, exiting the interaction with suppose 60 keV. I will remind you that the fundamental law of conservation of energy must apply here also. The electron entered with 90 keV and exited with 60 keV. This means exactly 30 keV of kinetic energy was lost during that gentle breaking process. This lost energy is instantly converted into a brand new electromagnetic wave. You can see this newly born Bremsstrahlung photon radiating away with an exact energy of 30 keV. I want you to understand the clinical significance of this specific interaction. Because the nucleus is incredibly small and the atom is mostly empty space, these distant passes are extremely common. Distant passes means electron entering far away from the nucleus. This is exactly why the vast majority of your raw clinical X-ray beam consists of these lower energy photons. This is a very important observation to remember. We will notice this observation again later. We will study the entire spectrum of X-ray photon. In our next animation, I will show you the third and final scenario, which involves a direct head-on collision. This is the third and final scenario of Bremsstrahlung radiation production. This is a very rare but extremely important event. I will show you exactly what happens when the incoming electron makes a direct head-on collision with the positive nucleus. Please look at the dramatic interaction currently on your screen. Our incoming electron arrives from the cathode with an initial kinetic energy of, say, for example, 100 keV. Instead of passing by at a distance or near the nucleus, it travels straight into the center of the atom. Because it hits the massive nucleus directly, the high-speed electron is violently stopped in its track. This break is very sudden. The incoming electron loses its entire 100% of its kinetic energy in one single moment. According to the fundamental law of total energy conservation, this massive amount of lost energy cannot simply vanish. It is instantly converted into a brand new electromagnetic wave. This single photon is born with the absolute maximum possible energy. As you can see clearly on the diagram, exactly 100 keV goes in and a Bremsstrahlung photon of exactly 100 keV comes out. I want you to remember this specific physics rule for your exams. If you set your X-ray tube machine to exactly 100 kV, the maximum energy of any single photon produced will be exactly 100 keV. This rare direct hit determines the absolute maximum energy limit of your entire treatment beam. Now that you understand how these individual photons are born, I will teach you how to look at the complete clinical spectrum. Let me summarize these three specific scenarios of Bremsstrahlung radiation production for you. These three scenarios are so critical for your clinical foundation that I will teach you it to you twice. Please direct your attention to the diagram currently on your screen. See first scenario. We can call it a distant pass. When high-speed electron travels far away from the positive nucleus, it loses only a small amount of kinetic energy. This produces a low frequency and low energy photon. Next scenario, we can call it close pass. When the high-speed incoming electron travels closer to the nucleus, the invisible braking force becomes much stronger. This moderate loss of energy produces a high frequency and high energy photon. Finally, the third scenario, we can call it direct hit. Here, the high-speed incoming electron hits nucleus, making head-on collision. The electron loses its entire 100% kinetic energy in one single collision. This produces the maximum possible energy photon, which is perfectly equal to your machine's kilovoltage setting. The fundamental rule I want you to memorize right now is very simple. The closer the nucleus gets to the highly charged nucleus, the stronger the braking force and higher the energy of the resulting X-rays. See these exact three scenarios in a slightly different visual format. In scenario 1, you can clearly see the electron entering distantly from the central nucleus. In scenario 2, the incoming electrons enter much closer to the target. In scenario 3, the electron travels directly toward the absolute center for a head-on collision. I am repeating this because you must never forget how physical distances dictates clinical energy. Because this exact distance is completely random for every single electron, your machine will always produce a heterogeneous beam containing multiple different energies. In my upcoming slides, I will show you exactly how we graph this raw spectrum for your daily clinical use. On this slide, I want to explain you the physics of probability that dictates the behavior of your clinical X-ray beam. I want to explain this very slowly and clearly because it is the core reason your X-ray beam has varying energies. Look at the detailed diagram currently displayed on your screen. It shows exactly why our machines produce such a large quantity of low energy photons. You can clearly see multiple dashed lines coming from left, representing a stream of incoming high-speed electrons. See these. Notice the vast amount of empty space surrounding that tiny central nucleus. Because the positive nucleus is incredibly small compared to the total volume of the atom, such direct hits are statistically very rare. If you look at the paths on your screen, only one single line makes a direct head-on impact. This one. This single rare event produces the absolute maximum energy photon. Now, look at 4 lines that pass relatively close to the central nucleus. These 4, 2 above and 2 below, these ones. These close passes create the high energy photons, but they are still quite uncommon event. Finally, look at the remaining 45 lines that travel very far away from that center. These ones. Because the target atom is mostly empty space, these distant passes are by far the most common interaction. These distant electrons experience a very weak, invisible braking force. Therefore, they only lose a very small amount of their kinetic energy. This means the vast majority of Bremsstrahlung photon produced inside the machine will always be these low energy X-rays. Now that you perfectly understand this probability, I will teach you how to graph this exact spectrum for your daily clinical use. This is the visual representation of our unfiltered Bremsstrahlung X-ray beam spectrum. On the vertical y-axis, you can see the total number of photons produced. On the horizontal x-axis, you see the exact energy of those newly born photons. I will show you exactly how our previous 3 scenarios we saw in detail can be understood on this graph. This is an atom. This is nucleus, and these are electrons revolving around the nucleus in their respective orbits. See this curve. It is the entire spectrum of Bremsstrahlung X-ray beam. Now first look at the far right side of the curve. I want you to look at the height of this curve in this region. This is small. I want you to understand why this curve is small. As we discussed earlier, a direct hit with the incredibly small nucleus is statistically very rare. See this electron hitting nucleus directly head-on. Because it is so rare, you can see that very few maximum energy photons are actually produced. If an incoming electron carrying exactly 100 kilo electron volt makes a direct hit, it loses its entire kinetic energy and creates exactly one single photon of 100 keV. This specific rare interaction determines the maximum energy limit of your entire beam. Now, look at the massive red peak on the left side of your bar, of your graph. Here, the vast majority of target atoms consist of completely empty space. Because of this vast empty space, peripheral passes that occur far away from the nucleus are extremely common. See these so many incoming electrons away from the nucleus. Look at this incoming electron very far away at the periphery of atom. When these incoming electrons enter the atom away from the nucleus, they experience a very small, weak braking force and lose very little energy. This means your X-ray machine naturally produces a large quantity of very low energy photons. This is the reason you get this steep curve of Bremsstrahlung X-ray spectrum. This is called the raw unfiltered spectrum of Bremsstrahlung X-ray radiation. In this spectrum, you are seeing very low amount of high energy photons and very large amount of low energy photons. Pause this video and think about this. Now listen to me very carefully. If we were to use this raw unfiltered beam on a patient, these weak photons would only drastically increase the skin dose unnecessarily. They have absolutely no power to penetrate deep into the body to treat our tumors. These are useless and unwanted photons. Therefore, in my next slide, I will show you exactly how we can filter this raw beam to make it clinically safe. See here. These are photons from the raw, unfiltered spectrum of Bremsstrahlung X-ray moving towards right. There are some high energy photons and lots of low energy photons. We don't want low energy photons and hence wants to remove them. How can we do it? We do it by placing a filter here in the path of these X-rays. What happens when we place a physical filter in the path of this raw X-ray beam? Please direct your attention to the yellow filter currently displayed on your screen, this one. Our primary goal here is to completely remove the weak and low energy X-ray from this X-ray treatment beam. As I mentioned before, these low energy photons are extremely dangerous for our patients. They have absolutely no power to penetrate deep into the body or to treat tumors. They will only drastically increase the unnecessary radiation dose to the patient's skin. I will show you the exact physics of how this selective absorption works. Notice the specific mathematical equation displayed on the left side of your screen. The most important part of this formula is the photon energy raised to the power of 3 in the denominator. This simple physics rules tells us that the probability of a photon being absorbed drastically decreases as its energy increases. Because of this natural rule, our filter acts like a highly selective barrier. It easily catches and completely absorbs the weak, low energy photons. At the exact same time, it allows the powerful, high energy photons to safely pass straight through. See, some of this filtration happens naturally inside the machine itself. The glass envelope of the X-ray tube, the insulating oil, and the exit window provide what we call inherent filtration of the machine. We also add extra metal sheets to further clean the beam and make it perfectly safe for daily clinical use. This crucial process of removing low energy photons to increase the overall average energy of the beam is called beam hardening. This is how the Bremsstrahlung X-ray radiation spectrum looks like after the filter is applied. This is the filter. Notice now the beautifully refined red curve after it passes through this filter. Notice very carefully the shape of the curve. This specific curve represents the actual filtered beam that you will use to treat your patient in LINAC or take X-rays of your patient in radiology department. Notice how the entire left side of the raw spectrum has completely disappeared. Because of our inherent and added filtration, almost all weak photons are completely absorbed before they can ever reach the patient. I will explain the two most important concepts regarding this final curve. First, look carefully at the absolute hard right limit of this curve. This exact point represents the absolute maximum photon energy existing in your treatment beam. I want you to remember that this maximum energy is dictated solely by your kilovoltage peak setting in the machine. Second, look at the total red area completely enclosed under this curve. This mathematical area represents the total volume or total quantity of useful X-rays produced by your machine. This total volume is dictated by a combination of your kilovoltage, your tube current, your target material, and your added filtration. By understanding and controlling these specific physical factors, you transform a highly raw, unfiltered X-ray beam spectrum into a perfectly safe and penetrating clinical X-ray beam. Let me summarize our entire discussion by comparing these two graphs of Bremsstrahlung radiation spectrum side by side. First, look at the spectrum of a raw, unfiltered Bremsstrahlung X-ray beam on the left side. Raw, unfiltered Bremsstrahlung X-ray beam. Notice its shape. It is a curve with slanting shape. Look at the vertical y-axis. This y-axis shows the total number of photons, which means the total amount of X-rays produced. Now look at the horizontal x-axis. The x-axis shows the exact energy of those newly born X-ray photons. Look closely at the 5 different lines entering from the left. These lines represents incoming electrons traveling from the cathode. These 5 electrons have different energy levels. This is the central nucleus. Now look at the different fading red colors around the central nucleus. These fading red colors do not mean electron shells. They show the exact strength of the invisible magnetic pull at different distances from the nucleus. Once again, they show the exact strength of the invisible magnetic pull at different distances from the nucleus. The dark red center shows a very strong pulling force. The light red outer area shows a much weaker pulling force. You can clearly see how the 5 electron paths travel through these different pulling forces. The top path is very far from the nucleus. This one. It travels through the weak outer area, so it only slows down a little bit. The braking force here is small, and this creates a very low energy Bremsstrahlung radiation photon. As we move down the electrons, the electron gets closer and closer to the nucleus. These closer electrons feel a much stronger braking force. Therefore, they produce much higher energy Bremsstrahlung radiation photon. Finally, look at this electron which has hit the nucleus directly head-on, straight into the exact center of the nucleus. This is a very rare direct hit. If your machine is set to exactly 100 kilo electron volt, this direct hit will transfer all of its energy. It creates just one single photon with the maximum energy of exactly 100 kilo electron volt. But we know that the atom is mostly empty space. Because of this, electron passing away from the nucleus are much more common. This is exactly why your raw, unfiltered beam is full of low energy photons, which are unwanted and unnecessary. So this is a slanting shapes Bremsstrahlung radiation spectrum you get from raw, unfiltered beam. Now look at the second graph on the right side of your screen. This is what happens when we place a metal filter into this raw beam. You can see the yellow filter placed directly in the path of the X-rays. If we use the raw beam directly on a patient, their skin will simply absorb all those low energy photons. These weak photons cannot go deep into the body to treat the tumor. They may damage the patient's skin. Therefore, our filters acts as a very smart safety filter. The physics rule here is very simple. High energy photons will easily pass through the filter, but low energy photons will get trapped or filtered. Because of this rule, the filter easily stops and absorbs those dangerous weak photons on the left side of the graph. At the exact same time, it allows the strong high energy photons to pass safely to the patient. Notice how the straight raw line has completely changed its shape to this shape once the filter is applied. This yellow thing is filter. The resulting curve has now become a smooth bell-shaped curve. This process of removing weak low-energy X-ray photons to make the beam stronger is called beam hardening. By filtering the raw beam, we get a safe, deep penetrating beam that you will use to treat your patients every single day or take an X-ray in radiology department. Let us look at the final results of this filtration process. Please take a screenshot of this image and study it carefully to understand how a raw, unfiltered X-ray beam is converted to filtered, clinically usable X-ray beam. This specific curve represents the actual filtered Bremsstrahlung X-ray radiation beam that is ready for you to use on your patient for either imaging in radiology department or for treatment in radiation oncology department. Notice how the entire left side of the raw graph has completely disappeared. Almost all of the dangerous low energy photons below 12 keV have been safely absorbed by our filters. In reality, it is practically impossible to have a completely raw beam because of the inherent filtration inside the tube itself. Now look at where the red curve touches the horizontal axis on the far right side. This specific point represents the absolute maximum photon energy of the entire beam. Next, look at the total colored area under this specific curve. This entire area represents the total quantity of useful X-rays produced by your machine. This total quantity is determined by a combination of your kilovoltage peak and milliamperes, your target materials, and your total filtration. By changing these specific physical factors, you can completely control the quality and quantity of your clinical beam. With this, I finish our discussion on Bremsstrahlung radiation. In my next slides, I will introduce you to our second major mechanism of X-ray production, which is called characteristic radiation. In our previous slides, I taught you the complex physics of Bremsstrahlung X-ray radiation production. As I mentioned earlier, less than 1% of the incoming electron energy actually becomes useful X-rays. While the vast majority of those X-rays are Bremsstrahlung, a very small and specific fraction is produced through a completely different mechanism. This unique mechanism creates what we call characteristic radiation. I'm going to teach you exactly how this different interaction happens inside the X-ray tube when a high-speed incoming electron strikes tungsten target. Unlike Bremsstrahlung X-ray production process, this specific process absolutely does not interact with the nucleus. Instead, it involves a direct collision with the inner orbital electrons of our target material. Inner orbital electrons. This is a very important concept you must know. So I want you to pay very close attention. Let me break down the exact mechanics of this interaction for you step by step in my upcoming slides. Let us once again look at the structure of our target atom. This is our classic model of heavy tungsten atom. In our previous discussion about Bremsstrahlung, we focused entirely on the heavy central nucleus. But for characteristic X-ray radiation, our focus must completely shift away from that positive center. Instead, we must look very closely at the negative orbital electrons. Notice how they are perfectly arranged in their specific energy shells. You can clearly see the innermost K shell followed by L, M and N shells as we move outward. I want you to remember a very important point here. Characteristic radiation is a direct interaction between the incoming bombarding electron from the cathode and these specific orbital electrons of the target. Once again, characteristic radiation is a type of interaction which happens between the incoming bombarding electron from the cathode and these specific orbital electrons of the target. This specific microscopic process completely ignores the central nucleus. In my upcoming slides, I will show you exactly what happens when our incoming high-speed electron collides directly with one of these tightly bound inner electrons. I want you to fully understand the critical concept of binding energy. Again, before we move forward, binding energy is simply the invisible holding force that keeps these negative electrons safely in their specific orbits around the positive nucleus. Notice the exact numerical values listed next to each individual shell for tungsten target metal. The outermost N shell has a very weak binding energy of only 0.6 keV. As we move inward, the L shell has a much stronger binding energy of 10.2 keV. Finally, look at the innermost K shell. Because it is located right next to the heavy positive nucleus, it has an extremely strong binding energy of exactly 69.5 keV. The fundamental physics rule here is that binding energy always increases as the electron gets closer to the central nucleus. Now, why this specific number is so incredibly important for us? In order to successfully knock a tightly bound K-shell electron completely out of its orbit, the kinetic energy of an incoming high-speed electron must be stronger than the binding energy of this tightly bound K-shell electron. The bombarding electron arriving from the cathode must possess a kinetic energy strictly greater than 69.5 keV. If your incoming electron carries anything less than this exact energy, it will simply bounce off without creating any K-shell characteristic X-ray. This incoming kinetic energy is determined entirely by your machine's kilovoltage peak setting. Now let us see the exact step-by-step collision when a powerful incoming electron successfully dislodges this inner target. This is atom and its components: the nucleus, orbits and orbital electrons. You can see a yellow dot representing our incoming high-speed incident electron. This high-speed electron is arriving directly from the heated cathode filament of X-ray tube. See here in this X-ray tube. I want you to imagine this incoming electron acting exactly like a fast-moving cue ball on a pool table. Imagine this specific high-speed incoming electron has kinetic energy greater than the binding energy of the tightly bound K-shell electron, that is 69.5 keV. Because it has this massive energy, it is powerful enough to break the strong holding force of the target atom. It is traveling straight towards the target material, completely ready to invade the inner electron shells. Let us see exactly what happens as this powerful electron enters the atom. This is the exact path of this powerful incoming electron. The electron is entering the atom. Watch very carefully as it easily penetrates the outer electron shells of the target atom. Notice how it completely ignores the negative electrons floating in those outer orbits. These outer electrons have a very weak binding energy, so they cannot stop this powerful incoming electron having high energy in the form of high kinetic energy. Because this bombarding electron is carrying a massive kinetic energy of more than 69.5 keV, it easily passes right through these outer layers. It is traveling deep into the atomic structure, heading directly towards the innermost K shell. This specific interaction completely ignores the heavy positive nucleus. This fast-moving electron is on a direct collision course with a tightly bound inner orbital electron. Now I will show you exactly what happens when this powerful direct collision finally takes place. This is the exact moment of impact. You can see that the fast-moving incoming electron finally hits the innermost K shell. It makes a direct head-on collision with one of those tightly bound orbital electrons in K shell. I remind you here that for the tungsten target, this specific shell has a very strong binding energy of exactly 69.5 keV. Because the incoming electron arrives with a kinetic energy strictly greater than 69.5 keV, it easily overpowers this holding force. It transfers its kinetic energy directly into the resting K shell electron. This is the direct result of this powerful collision. Because the incoming electron carries a kinetic energy greater than the binding energy, it successfully overpowers the strong nuclear pull. It violently knocks the inner electron completely out of its orbit. Notice the newly ejected electron flying away. Now, I want you to look very closely at the K shell where the tightly bound electron used to be. This is now a complete vacancy, which is clearly represented by the empty white circle. See here. This sudden empty space leaves our entire target atom in a highly unstable and unnatural state. Let us see exactly how the atom naturally reacts to fix this instability. This is the exact paths of these electrons immediately after the collision. You can clearly see two separate electrons exiting the atom. The first electron flying towards the top right is our newly ejected target electron. It has been completely removed from the atomic structure. The second electron shown below is our original bombarding electron. After violently transferring its kinetic energy, it is deflected away on a completely new path. Because this inner electron was forcefully removed, there is a gaping hole in the innermost shell. This empty hole is clinically referred to as a vacancy. I want you to thoroughly understand that nature does not like empty spaces in these inner energy levels. This specific vacancy makes our entire target atom highly unstable. Watch exactly how the atom fixes this instability. Please keep your eyes on the outer L shell of the atom currently on your screen. As I mentioned earlier, nature absolutely does not like empty spaces in these inner energy levels. Because the innermost K shell is completely empty, the atom remains in a highly unnatural state. To heal this empty space, an electron from the higher L shell immediately drops down to fill this vacancy in K shell. You can see the specific outer electron falling into the inner K shell right now. By filling this vacancy, the target atom successfully stabilizes itself. But we must remember a very important rule of physics here. An electron residing in the L shell naturally holds much more energy than an electron in the K shell. Therefore, it cannot simply sit in the lower energy shell with all of that extra power. In order to perfectly fit into this lower space, the dropping electron must shed its excess energy. Once again, in order to perfectly fit into this lower space, the dropping electron must shed its excess energy. This is what happens to that extra energy. As the outer electron drops into the inner K shell, it moves from a higher energy state to a lower energy state. According to the fundamental law of energy conservation, this excess energy cannot simply vanish. It must be completely shed by the dropping electron. This released energy bursts out as a precise electromagnetic wave. You can clearly see this newly born X-ray photon exiting the atomic structure. We call this specific type of photon a characteristic X-ray. Characteristic X-ray. I want you to fully understand exactly why we use the word characteristic. The exact energy of this single photon is perfectly equal to the mathematical difference between the binding energy of those two specific shells. Because every single element has its own unique set of electron shells, these binding energies are completely different for every element. Therefore, the energy of the resulting X-ray acts as a precise physical fingerprint for a specific target material. If an outer shell electron drops into a K shell vacancy in a tungsten atom, it will always produce a characteristic photon of exactly the same energy. These specific photons are always created at highly predictable and discrete energy levels. I hope you understand characteristic radiation. Let me show you an animation on one single slide to show how a characteristic radiation is produced. This is a stable atom. The incoming bombarding electron is arriving toward the atom. I want to remind you that its kinetic energy is completely determined by your machine's kVp setting. In order to produce useful characteristic X-ray in your tungsten target, this specific energy must be strictly greater than 69.5 keV. Watch very carefully as this powerful electron penetrates the outer shells. It makes a direct kinetic transfer by striking the tightly bound K shell electron head-on. Because the incoming energy is massive, the inner electron is violently ejected from its normal orbit. Notice the empty white circle that is suddenly left behind in the innermost shell. This specific vacancy leaves our entire target atom in a state of instability. The atom is now unstable or unstable. You can also see how original bombarding electron deflecting downward on a completely new path. Now I want you to watch exactly how nature heals this unstable atomic state. Watch carefully. An outer shell electron drops down to fill that critical vacancy. But because it is moving from a higher energy state to a lower energy state, it carries too much energy to simply sit there. In order to successfully stabilize the atom, this dropping electron must immediately shed its excess energy. Notice this excess energy bursting out of the atom as a bright green electromagnetic wave. This specific wave is our characteristic X-ray photon. Finally, please look at the simple mathematical equation that just appeared on your right side of your screen. The exact energy of this newly born photon is perfectly equal to the binding energy of the inner shell minus the binding energy of the outer shell. Because these exact binding energies are completely unique to every single element on the periodic table, this resulting X-rays acts as a precise physical fingerprint. I want you to memorize this exact sequence of characteristic X-ray production. Why do we actually call this characteristic radiation? Let me explain this with a simple comparison on your screen. On the right side, you see our familiar tungsten atom. It has an atomic number of exactly 74. When an electron drops from the L shell to the K shell here, it releases a photon. That specific photon has an energy of exactly 59.3 keV. This is equal to the energy difference between the binding energy of K shell and binding energy of L shell. That is 69.5 keV minus 10.2 keV equal to 59.3 keV characteristic X-ray photon. Now look at the completely different atom on left side of your screen. Here we have a target material called molybdenum. Molybdenum has a much lower atomic number of just 42. This means it has fewer positive protons pulling on its electrons. Because this pulling force is weaker, its binding energies are much lower. Its inner K shell only has a binding energy of 20 keV. Its L shell is even weaker at just 2.6 keV. When an electron drops between these two specific shells in molybdenum, the energy difference is much smaller. It releases a photon of exactly 17.4 keV. 20 keV minus 2.6 keV equal to 17.4 keV characteristic X-ray photon. I want you to really think about what this means for us clinically. The exact energy of these X-rays produced is completely controlled by the number of protons in the nucleus. Every single element in the periodic table has its unique set of binding energies. Because of this, the emitted X-ray photon acts exactly like a fingerprint for that particular element. By simply measuring the exact energy of the photon, we instantly know which target metal created it. This is exactly why we use the word characteristic. It is perfectly characteristic of the specific element used in our target. Now, let us move to the next slide to see what else can happen when that inner shell is empty. Let us now look at another very important competing process. We just learned that an inner shell vacancy leaves our target atom highly unstable. I want you to firmly understand that the atom actually has two different ways to fill up this vacancy. The first way is exactly what I just taught you in our previous slides. An outer electron drops down and simply releases its extra energy as a characteristic X-rays. We have seen that just now. But there is another completely different pathway called the Auger effect. Auger effect. In this specific scenario, the atom does not release any electrostatic radiation at all. Instead, the dropping electron transfers its excess energy directly into another orbital electron inside the exact same atom. Because this receiving electron suddenly gains a massive amount of kinetic energy, it is violently ejected from the atomic structure. We clinically refer to this ejected particle as an Auger electron. I want you to be very clear for your understanding that these two specific outcomes are perfectly mutually exclusive. The healing energy is either radiated outward as a photon or it is transferred internally to eject an Auger electron. The atom absolutely cannot do both at the same exact time. By understanding this competent pathway, you now have a complete clinical picture of these atomic interactions. Let us now see how we draw these characteristic X-rays on a graph. We have earlier drawn Bremsstrahlung radiation. Now we draw characteristic X-ray on a graph. On the right side, you can see atoms, its nucleus, and its various orbits K, L, and M. These green dots are high-speed incoming electrons coming towards this atom. See our tungsten target atom being hit by these high-speed incoming electrons. Notice that these incoming electrons arrive with an energy of exactly 100 keV. I am reminding you that this energy is completely controlled by your kVp setting. Because 100 kVp is much greater than the K-shell binding energy of 69.5 keV, these electrons can easily knock out the inner targets. Now look closely at the two different blue wavy lines coming out of the atom. These ones. Listen now. If an outer electron drops from the L shell down into the K shell, it creates what we call a K alpha photon. From the L shell down into the K shell, like this. If an electron drops from the M shell all the way down into the K shell, it creates a K beta photon. From the L shell all the way down to the K shell. See here. Because the M shell is further away, the electrons falls a longer distance. This longer fall creates a larger energy drop, making the K beta photon slightly stronger than the K alpha photon. Now please look at the graph. Look at the horizontal axis, which shows the exact energy of the X-rays. You can clearly see two very sharp, tall blue lines standing straight up. This one and this. These two sharp spikes perfectly represents K alpha and K beta X-rays. This is a very important point for you to understand characteristic radiation. Characteristic radiation does not create a wide shape with many different energies. Instead, it creates X-rays only at a very specific exact energy numbers. I want you to firmly remember that for tungsten target, these exact spikes will always appear at these exact same places on this graph. I hope I was able to explain you characteristic radiation. You need to watch it a few times to understand it clearly. Let us now combine everything we have learned to build our complete clinical X-ray beam. Before we add our new characteristic spikes, we must quickly remember what our Bremsstrahlung spectrum looks like. On the vertical axis, you can clearly see the total photon number. On the horizontal axis, you can see the exact photon energy, photon number and photon energy. This smooth red curved shape perfectly represents our filtered Bremsstrahlung radiation. Notice how the curve starts from the low energy side on the left. The weak X-ray photons are missing here because they have already been safely removed by the filter. Now please direct your attention to the high energy side on the far right. Look at the exact point where the curve finally touches the baseline. This one. This specific point is the absolute maximum photon energy of your entire beam. In this exact example, it reaches a maximum energy of exactly 100 keV. I will remind you again that this absolute maximum energy limit is controlled entirely by your machine's kVp setting. Please listen to me very carefully. This beautifully smooth curve clearly proves a very important clinical fact. Our clinically used X-ray beam is not made up of just one single energy photon. It is a completely heterogeneous beam containing many different energy level photons. Once again, our X-ray beam is not made up of just one single energy photon. It is completely heterogeneous beam containing many different energy level photons. This clinically used X-ray beam is not perfect monoenergetic, but it is polyenergetic. Although we have removed most of the lower energy photons using filter, but still we don't get a perfect monoenergetic beam. Now that our basic foundation is completely ready, we can now finally add our characteristic X-ray on this graph. In my next slide, I will show you exactly how we combine those sharp spikes of characteristic radiation with our Bremsstrahlung curve to create the final beam for your patients. Look closely at these two new vertical lines that just appeared on your screen on Bremsstrahlung X-ray spectrum curve. You can clearly see these two sharp spikes standing directly on top of our smooth red curve. See these. These sharp vertical spikes represents our characteristic radiation. Notice how they are labeled specifically as K alpha and K beta. As we discussed earlier, these spikes only happen at very specific exact energy numbers. I want you to carefully look at these complete picture. This combined graph is what we clinically call the total X-ray spectrum of clinically ready to use X-ray radiation beam. The wide, smooth red background represents your Bremsstrahlung radiation spectrum. It has some low energy photons, although we have removed them using filters, and have high energy photons. The tall sharp spike represents characteristic radiation. I will remind you again that for a tungsten target, these spikes will always appear in the exact same position on the graph. Whenever you press the exposure button on your clinical machine, this combined beam is exactly what comes out of the tube. You will be asked about this graph in your physics viva over and over again. Because it is so important, I highly recommend that you draw this complete spectrum in your mind right now. Let us look at these specific graphs to understand the complete X-ray spectrum of our clinical beam to ensure that we understand it 100% now. This is the final ready-to-use clinical X-ray beam spectrum. You are seeing a smooth rounded shape with very sharp tall spikes standing right on top of it. This combined picture is exactly what your final X-ray beam looks like. The large continuous background curve represents your Bremsstrahlung radiation. Remember that Bremsstrahlung produces a wide mixture of many different energy levels. Look very closely at those sharp vertical lines. These exact spikes perfectly represents characteristic X-ray photons. Unlike Bremsstrahlung, these photons do not have a wide range of random energies. They are created only at highly specific and exact energy levels. I want you to firmly remember that these exact positions on the graph are completely dictated by the atomic structure of your target material. For our standard tungsten target, the most important spikes will always appear between 57 and 59 keV for the K alpha photons. If you look at the similar X-ray spectrum of a different target material element, for example molybdenum, because molybdenum has a much lower atomic number, its binding energy are much smaller. Therefore, its characteristic spikes will appear much earlier on the horizontal energy axis. This proves that these spikes act as a precise physical fingerprint for the target element. Even if you increase your kilovoltage setting, the horizontal position of these characteristic spikes will absolutely not change. Increasing your kVp will only push the absolute maximum energy limit of the smooth Bremsstrahlung curve further to the right. Understanding how to physically read these specific graphs is absolutely critical for your understanding of radiation physics. I want you to practice drawing this complete spectrum to itself. I have selected these images from the various standard physics textbooks and study materials. At first glance, they might look a little bit different from each other in their drawing style or their color. However, I want you to look very closely at their basic shapes. You will notice that every single one of them shows the exact same fundamental physical concept. They all feature that They all feature that wide, smooth background curve representing our Bremsstrahlung radiation, and they all feature those tall, sharp vertical lines representing our characteristic X-ray spikes. Do not let these different drawing styles confuse you. No matter which textbook you are reading from, they all perfectly represent our complete clinical X-ray spectrum. By fully understanding the basic physics behind these shapes, you can confidently read any graph your examiner gives you. Let us now summarize everything we have learned today. This table directly compares our two distinct methods of X-ray production. I want you to pay very close attention to each of these specific points. These differences are absolutely must remember point for you. First, let us look at the exact target site for each interaction. For Bremsstrahlung radiation, the incoming electron interacts directly with the heavy positive nucleus of the target atom. But for characteristic X-ray radiation, the incoming electron completely ignores the nucleus. Instead, it interacts directly with the tightly bound inner orbital electron. Next, let us compare the exact atomic mechanism. In Bremsstrahlung, the incoming electron is strongly attracted by the positive nucleus. This invisible pull forces the electron to rapidly slow down and change its path. The kinetic energy it loses during the sudden braking maneuver is shed as an X-ray photon. However, the characteristic mechanism is completely different. The incoming electron forcefully ejects an inner shell electron completely out of its orbit. To fix this highly unstable empty space, an outer shell electron immediately drops down. It must shed its excess energy as a single X-ray photon to perfectly fit into the lower space. Now let us look at how these photons appear on our final emission spectrum. Bremsstrahlung creates a completely continuous and polyenergetic spectrum. It appears as a wide, unbroken bell curve containing many different photon energies. On the other hand, characteristic radiation is completely discrete and monoenergetic. It appears only as highly specific, sharp vertical energy spikes on our graph. What exactly controls the energy of these resulting X-rays? For Bremsstrahlung, the photon energy is controlled entirely by the distance from the nucleus. A closer interaction creates a much sharper turn and a much higher energy X-ray. But for characteristic radiation, distance from the nucleus does not matter at all. The resulting photon energy is perfectly equal to the exact mathematical difference in binding energy between the two specific electron shells involved. Let us see how much each processes contribute to our final clinical beam. I want you to firmly remember that Bremsstrahlung constitutes the vast majority of your useful X-ray beam. It makes up greater than 85% of total clinical beam. Characteristic radiation only contributes a very small percentage of less than 15%. These percentages number may vary depending on a lot of other things. But you should remember that the vast majority of clinically useful X-ray beam comprises of Bremsstrahlung X-rays and some minor portion by characteristic radiation. Next, we will look at how changing the target material affect each process. If we increase the atomic number of our target metal, we simply increase the total intensity of our Bremsstrahlung radiation. The wide continuous shape of the curve will remain exactly the same. But for characteristic radiation, changing the target metal changes everything. Because every single element has a completely unique sets of binding energies, these sharp spikes act as a precise atomic fingerprint. The energy level for a tungsten target will be completely distinct from a molybdenum target. Now let us discuss the activation threshold. Bremsstrahlung radiation does not have a minimum starting requirement. It occurs at absolutely any incident electron energy. Characteristic radiation, however, has a very strict activation rule. The incoming electron must carry an energy strictly greater than the binding energy of that specific inner shell. For our clinical tungsten target, this incoming energy must be strictly greater than 69.5 keV. Finally, let me give you two simple mental pictures to help you remember this. Think of Bremsstrahlung radiation exactly like a fast car, turning and braking sharply to take a very sharp turn. The speed that the car loses is just like the kinetic energy our electron sheds. Think of characteristic radiation exactly like a fast moving cue ball on a billiard table. The incoming cue ball violently strikes and knocks out that target ball completely out of its pocket. I strongly advise you to memorize this complete table. It forms the absolute foundation of your radiation physics. So friends, with this we have finished seeing how X-rays are produced from our clinical X-ray machine. But this is only half of the story for a radiation oncologist. The most important clinical question still remains. What exactly happens when these powerful photons leave the machine and finally enter our patient's body? In our next lecture, I will take you on a fascinating journey inside the human tissue. We will explore the exact microscopic interactions of ionizing radiation with matter. I will teach you exactly what happens or which interaction happens when these photons collide with a matter. We will look at the final fate of a photon. We will thoroughly discuss the major fates of photons: photoelectric effect, Compton scattering, and pair production. Understanding these specific interactions is the absolute key to everything we do in radiation physics. It perfectly explains how we successfully destroy cancer cells while safely protecting the normal surrounding tissues. These core concepts are heavily tested in every single physics exam. So please revise today's concepts carefully, and I will see you in our next session. Thanks for watching. See you next video. Signing off, Parveen Elawat.